Alright, let's solve this problem again. Now, a short version. No questions, no conversation, just the solution. So we have a board placed on two supports and another object is placed on the board. Pictures has to be converted into a diagram. So we have to show all the forces acting on, well, that's our object of interest, the board. So we see touching. That gives a normal force. Another touching. Another normal force. Now this object touches the board, so there has to be a force acting from this mass on the board, downward. As we know, every force has a source. No source, no force. There is one more object, the Earth, which exerts a force on this board, force of gravity, which is applied because the board is uniform to the middle point of this board. Now, to calculate the force of gravity acting on the board, we do this, 5 newtons. This force is a little bit tricky. So let's take a look at the enlarged picture. So there is a force acting from this mass on the board here. But because they touch each other, now, according to Newton's third law, there has to be a force acting back from this board on this object. That force should have opposite direction, but too short, oh, exactly same magnitude. We still don't know this force, but this force now is acting on this object. If we had only one force acting on this object, it would speed up, flying away. That's not happening because this object is also in equilibrium. That means there has to be another force acting on it. That, of course, is again force of gravity. And this force is equal to mg, different m, same g, 3 newtons. Now, because this object is in equilibrium, these forces must have the same magnitudes. They have to cancel each other. Newton's second law gives zero acceleration. So this also 3 Newton force. But now, according to Newton's third law, these two forces also must have the same magnitudes. So 3 Newton force. And these are the unknowns. Well, don't really like this picture. Let's just draw a diagram, free body diagram, just forces. 5 newtons, 3 newtons, unknown force, unknown force. Well, equilibrium. That means net force acting on this object is equal to 0. Net torque acting on this object is also equal to 0. Net force, if we choose positive y direction, as usual, upward, should be equal to normal 1 minus 5 minus 3 plus normal 2. Unfortunately, 2 unknowns. That has to be equal to 0 because of this. But still, we gotta do something else. And now, a second condition can be used. But to use it, we must add one additional element to this picture. And that is the origin. Where can we choose the origin? Anywhere. So we can choose it here, 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 even here or there. So let's just choose it again. according to the rule of thumb, at the location of the unknown force. So now, relative to this origin, to this axis of rotation, we can write the magnitude for this torque, this torque, this torque, and this torque. Well, torque due to this force, this force, this force, and that force. All right. The magnitude of this torque times, well, of course, the individual torque of each force is equal to this magnitude of the force, the lever arm of that force relative to the origin or axis of rotation. So we don't know this force, but we cannot leave this space empty. We have to write something, and we write the symbol, label. But this should represent the distance from the axis of rotation to the line of action. Do you see any distance? No. No distance. No means zero. No torque. The force is not zero, but the torque of that force relative to this axis is zero. Moving on. Next. Torque is due to force of gravity acting on the board. Well, the force is 5. Now, the line of action, that's going to be the shortest distance from the axis to the line. And, well, now we got to use some simple geometry. The whole board is 50 centimeters long. So the force of gravity is applied to the middle of this board because it's uniform. That means this should be equal to 25. A half of a board minus 5. That's 5 centimeters. Remember from the picture, that also is 5 centimeters. That's 5 centimeters. So 25 minus 5, 20 centimeters, or 0.2 meters. So 1 Newton times a meter. Done. Next magnitude. 3 Newton force. The magnitude is 3. Now we need a distance. Which distance? Not this. We have to measure the distance from the same axis to the new line of action. And that's going to be 25 minus 5 plus 5 again. So 25 centimeters or 0.25 meter or 1/4, 3 over 4, 0.75 Newton times a meter. And finally, one more magnitude of the torque due to that force. We don't know the force again, so we have to write something which represents the magnitude of it. And we need to multiply by the lever arm, which is shortest distance from the axis to this line of action, which is this. Well, that's going to be 50 minus 5 minus 5, 40, or 0.4. And that's it. Well, before starting using this equation, we have to make a statement about each torque. Is it positive or negative? If it's not zero, well, that's zero. But next one, positive or negative? Well, that depends. Relative to this axis, it tries to move it clockwise, which makes it negative. Of course, same here, also negative. But this one tries to move it counterclockwise, and that makes it positive. So we have 1 zero torque, 2 negative torques, 1 positive. Well, that literally means this torque has a negative component relative to the z-axis. This torque has a negative component relative to the z-axis, and that means the arrow representing this torque points into the page away from us. Arrow which represents this torque points into the page away from us, but arrow which represents this torque points out of the page toward us. But if we add them up all together, 0 plus -1 plus negative 0.75 plus positive this, that should be equal to net torque. And because the board is in equilibrium, that has to be equal to 0. So now, of course, we can quickly calculate this force. So 1.75 over 0.4. 4.375, and that's newtons. Well, are we done? Not yet. We need to calculate one more force, but now we can use this equation, which didn't work originally, but now, since we have found one more variable, we can solve this equation. Normal number 1 will be equal to 8 minus 4.375, which is 3.625 newtons. And now we are done.